nanoHUB-U, online instruction.
Welcome back to Unit 4 of our course on quantum transport. This is the third lecture. So as you may remember, in the last lecture, we considered a device with just one point, one basis function, and including spin then, the matrices that describe it are 2 by 2 matrices. And we assume the channel itself is non-magnetic, and so the Hamiltonian matrix describing the channel, that's like epsilon times I. So it's epsilon on the diagonal because up and down are both equivalent. But when we try to write the matrices describing the connection to the contacts, that's the sigmas and the gammas, that's when we have to distinguish between up spins and down spins. One spin gets out easily, the other one doesn't. Now the question is, how would you write the gamma for a magnet that's pointing in some other direction? Now in the last lecture we argued that if the magnet is pointing in the opposite direction, you could just reverse the alpha and beta. So instead of alpha beta, you have beta alpha, because the role of up and down spins are exactly reversed. But what would you do if you had a magnet pointing in some other strange direction? That's what we'll talk about in this lecture. And this is where it's important to understand this important distinction between spinors and vectors. And as I mentioned in the introduction, one good analogy for electron spin is the polarization of light. And polarization of light you visualize in terms of vectors. You learn in freshman physics that light has this electric field which defines its polarization. And if you had a polarizer and an analyzer that are at 90 degrees, then it will block the light. Whereas if they are parallel, the light will flow easily. You could think in a similar way here. These magnets are like the polarizers and the analyzers. And if they are parallel, electrons flow easily. Lots of current, low resistance. If they are anti-parallel, that's when it's blocked. High resistance. But note this important difference with light. With light, if the polarizer and the analyzer were anti-parallel, that wouldn't block it. That is almost like being parallel. Light would go straight through. They are blocked when they're 90 degrees. 90 degrees is the orthogonal direction. But with electron spins, 90 degrees doesn't give a minimum. It's 180 degrees that gives a minimum. Those are the orthogonal directions. And that's why, I guess, with light, the polarization of light, you understand in terms of vectors. But with spins, you need something else. And that's what you call spinors. So with a vector, when you think of something pointing in some direction n, defined by the angles theta and phi, you can write its x, y, and z components as, cosine theta is the z component, sine theta is the xy component, and then you could resolve it again and write sine theta cosine phi, sine theta sine phi. That you learn in vector algebra. But if it's a spinor, you visualize it the same way. You think of it as pointing in some direction, but you do not write 3 real components for it. You write 2 complex components, an up component and a down component. And what are these components? Well, the components are cosine half theta and sine half theta. Exponential minus I phi half, exponential plus I phi half. Now, this isn't meant to be obvious. And in the next lecture, I'll try to justify this. But for the moment, let's just accept this and we'll talk about the consequences of it. Okay? So, but the main point to note is how here you had a theta and the phi, and here you have half theta and half phi. So with vectors, when you have something pointing in this direction, you can resolve it using this parallelogram law and write it as a superposition of this and this. With spinors, all the angles are this, instead of theta, it's half theta. So in order to get 90 degrees, you kind of need 180 degrees here to get orthogonal. And so a spinor pointing in this direction is resolved into this and this. which are at 180 degrees. So as if you see the angle got doubled. And so what that means is a spin pointing in the plus z direction is actually a superposition of a spin in the plus x direction and a minus x direction. You see, very counterintuitive, very different from vectors. And so it takes some time to get used to. And as we go along, we'll mention other non-intuitive issues. Now, one of the non-intuitive things that we'll address actually right away is this question of how would you write the components of a spinor or a vector that instead of pointing along plus n is pointing along minus n in exactly the opposite direction. So these two quantities I had written down before, I'll denote as C and S. So C and S denote the components of something pointing this way. So how do I write the components of something pointing the other way? Now if it's a vector, actually the answer would be very simple. You'd say, well, if you have a vector with pointing this way, anything pointing the other way, you just add a minus sign in front of it. So this vector and this vector, one is just the negative of the other. But that's not true of spinors. Spinors, as I pointed out before, this 180 degrees is actually an orthogonal direction. It's not just negative of the other one. Orthogonal means it cannot be expressed in terms of the last one. So to find the appropriate components, you have to go through it more formally. So formally what we can say is that when you go from plus n to minus n, what you're doing is you're turning theta into pi minus theta. That is, instead of being this angle, you're taking this and turning it on to here so that the effective angle is pi minus theta. And instead of phi, you're writing pi plus phi, which kind of rotates it to the appropriate direction. So you can think this through, but if you put those in, if you do those substitutions in the vector components, you'll get what you expect intuitively. Namely, x will become minus x, y will become minus y, z will become minus z. You can check that. But with the spinor, when we do that, what would happen is, instead of theta, we would put pi minus theta. Instead of phi, we would put pi plus phi. Same here. And now, you see cosine pi over 2 minus theta over 2, that's actually sine theta over 2. Similarly, sine pi minus theta over 2, that's like cosine theta over 2. And exponential minus I pi over 2, and here you have an exponential plus I pi over 2. So what I've done is taken I pi over 2 outside and put a exponential minus I pi over here. Okay. So just that substitution into this then gives you the appropriate expression for the components of minus n. And one point I want to make here is that when you write this components of a spinor, this overall quantity here does not matter. So if you put an exponential I pi over 2 or any phase factor out here doesn't matter. What matters is this relative phase between them. So we could write the minus n as just this, which is what I've written here, and this part, and the exponential I pi is a minus 1. So that's that. So, and the phase factor in front, that really doesn't matter. You could put anything in front. And as I said, this is something we'll justify a little better in the next lecture. But one point you might say, well, if you just can add anything, doesn't that cause big problems? I mean, after all, how do you interpret experiments? Doesn't the sign matter? And the answer is, you see, with the polarization of light described by an electric field, the sign matters because electric field is a measurable quantity. And if you say I can easily put a minus sign in front, that would make no sense. But with electron spin, you see there's the wave function, that's psi. But the observable quantity is psi dagger. And so, it doesn't matter what phase factor you put in front. The psi is different, but the psi dagger isn't. And so when you're interpreting experiments, it shouldn't matter what you put in front. Now you'll notice what I've written here, you could write as, this is really what I defined as C, but complex conjugated. And what I wrote here as S, complex conjugated, gives you that. And the point to note is, this is not just negative of that. So you couldn't express this as just some multiple of this. This is a totally independent thing. In fact, what you can show is this and this are actually orthogonal, in the sense that if you multiplied this by the conjugate transpose of that, you'd actually get 0. They're orthogonal things. Now, the next thing then, given this result, the plus n and the minus n, how would we use it to write down gamma 2? And there the argument goes like this, that you see, for a magnet pointing in the plus z direction, we have written gamma 1 in this form. Now, if we used plus n and minus n as our basis functions, then the matrix for gamma 2 would also look like that. In other words, gamma 1 looks like this because our basis functions are plus c and minus c. This magnet is identical, but it points, instead of pointing along z, it points along n. So if I use plus n and minus n as my basis functions, then of course it should look just like that. There should be no difference. Okay. But of course, what I'd like to know is, what does gamma 2 look like in the old basis, in plus z and minus c? And the way I can do that is, I can take this and do a basis transformation. And this is where, if you are rusty on basis transformations, you may want to look it up. Something you've seen in linear algebra. And the way it works with basis transformations is, you put a matrix here U, whose columns tell you what the old basis, which is plus n and minus n, what plus n is in terms of the new basis, plus z and minus z, which, as we discussed, is c and s. Similarly, you take minus n, express it in terms of z and minus z, that's this minus s star and c star. So this is the basis transformation matrix, and the way you do these transformation, the similarity transformation, is put u here and you put a u dagger there. And this is the conjugate transpose of this one. It also represents like what the plus z is in terms of plus n and minus n, what minus z is in terms of plus n and minus n. So how do I remember what to put on this side and what to put on that side? Well, that's where I've often pointed out that, you see, when you're multiplying matrices, it is the rows that multiply into columns. So if you have plus n minus n here, this also must be plus n minus n. Similarly, plus n minus n, this must be plus n minus n. On the other hand, if I had taken this thing and put it here, then you see what I'd have plus z and minus z over here, which wouldn't match that. And so that would be wrong. So the way you can line it up is by remembering that rows must match the columns. Rows must match the following columns. Okay. Now, once you have written this, then that tells you how to write down the gamma 2, and whatever we'll do after this will be just algebra. Multiplying them out, just prettying out the result a little bit, that's all. So if you multiply those two things, usual rule of multiplication, matrix multiplication is c times alpha minus s star times 0, so that's c alpha, c times 0 minus s star times beta, that's minus s star beta, and so on. So you can write the 2 by 2. Next, you can take this and multiply it with that, and that's when you get this matrix. C alpha times C star, that's C star alpha, minus S star beta times minus S, that's plus SS star beta, etc. So this is then the gamma 2. So you have done the multiplication. What I will now do is make it look a little prettier. So first thing we do is, for the C's and S's, we put in the actual, what it represents. So CC star, that's just cosine square half theta. SS star, that's sine square half theta. CS star, you see, that is this times the conjugate of that. That's like cosine theta over 2 sine theta over 2, which is half sine theta. And now you notice the phase factors don't cancel, because S star has an exponential minus I phi over 2. So when I multiply the 2, I get exponential minus I phi. Similarly, here I get the conjugate of that. And here again, if I just put in the numbers, I'll get that. So this becomes that. Next step is do a little more algebra, and you can show that this quantity is actually half alpha plus beta plus half alpha minus beta times cosine theta. Whereas this one is half alpha plus beta minus that quantity. So here what I'm using is again these trigonometric identities, which are that cosine square half theta plus sine square half theta is 1. And cosine square half theta minus sine square half theta is cosine theta. So making use of those identities, I get from here to here. Okay. Next, what I'll do is, we'll take this and break it up into 4 matrices, separate matrices. So what you can do is, first of those is alpha plus beta over 2 times the identity matrix. Because you'll notice there's an alpha plus beta over 2 here and an alpha plus beta over 2 there. So we have taken care of that. Next, you note there's an alpha minus beta over 2 cosine theta and a minus alpha minus beta over 2 cosine theta. So that I could write as alpha minus beta over 2 cosine theta and then plus 1 and minus 1. Plus 1 for this, minus 1 with this. So these two added together then take care of the diagonal elements. The off diagonal is still 0. For the off diagonal, what we note is, we first write the real part of this. The real part of this is alpha minus beta over 2 sine theta cosine phi. And you'll notice that real part is the same for this one as well. And so we have 1, 1. So this then gives me the real part of the off diagonals. And when you look at the imaginary part, that's when you have alpha minus beta over 2 sine theta, and then e to the power minus I phi is cosine phi minus I sine phi. So you have the sine phi here. And you get minus I plus I. So this matrix then can be written as the sum of 4 matrices, each one with its own component, own coefficient in front. This actually is generally true. You could take any matrix and write it in terms of any 2 by 2 matrix and write it in terms of these 4 matrices. See? Now, this is the identity matrix, and these 3 matrices are also known, they're given a name, and this is called the Z component of the Pauli spin matrix sigma. And NZ, that's of course the Z component of N, which is cosine theta. So we have alpha minus beta over 2, that cosine theta is NZ, and this then is the Pauli spin matrix, the Z component. Similarly, this is the Pauli matrix X, and sine theta cosine phi, that's just the X component of N. So you can write Nx sigma X. This is the Pauli spin matrix Y, sigma Y, and this is then the Y component of N. So you have Ny sigma Y. So you see you have I, then you have Nz sigma Z plus Nx sigma X plus Ny sigma Y, which you could write as sigma dot N. Because you remember when you have dot product of 2 vectors like A dot B, it means Ax Bx plus Ay By plus Az Bz. Similarly, sigma dot N denotes sigma X Nx plus sigma Y Ny plus sigma Z Nz. And what you could do is combine those two and write it in this form. You see, you could put the alpha plus beta over 2 outside. So then you'd have I. And here you would have alpha minus beta divided by alpha plus beta, which if you remember in the last lecture mentioned, you usually define as the polarization of the magnet. It tells you how effective a magnet is in terms of discriminating between the 2 spins. So the final result then is that the gamma 2 looks like alpha plus beta over 2, that's half the sum of the diagonal element, times this quantity, I plus P sigma dot N. So that's the basic result then of this lecture. And in getting there though, I introduced these Pauli spin matrices. And also I introduced this very non-intuitive concept of spinors that many of you haven't seen before. And as I pointed out, when a spinor points in some direction defined by theta and phi, its components are given by the C and S. And if it's pointing in the negative n direction, the components are not minus C and minus S, but rather it's minus S star and C star. And all these non-intuitive issues, I guess this I just stated without any justification. And in the next lecture, what I'll try to do is justify this a little better. Thank you.